This recording is my first time recording for the class, and I will appreciate if there's some grace on recording this. So chapter 12 is about alcohols and phenols. And my computer seems to be having problems in here. Okay. All right, apologize for that. So alcohols in general are molecules contain the group OH, which is oxygen and hydrogen together. We have the classic example of ethanol and cyclopentanol, but there are many other molecules which we refer to them as natural products that contain the alcohol group in it. These are two examples of them. And next slide, we have three more examples. In this case, we have cholesterol, which we don't think of it as an alcohol because we usually think of it as something that is not good to have high cholesterol, which is something related to non-polar compounds in general, but alcohols are polar molecules. So cholesterol has one side that is polar, one side that is non-polar. We have vitamin D that also contains an alcohol, and if you look closely, vitamin D resembles cholesterol. These three double bonds here will do an electrocyclization reaction in order to form cholesterol. So it's important for you to have vitamin D because then vitamin D gets converted to cholesterol, which is then is vital for the biosynthesis of many steroids. There's also geraniol here, which is used in perfumes. So many of the alcohols, if they are with double bonds, tend to give you very pleasant odors. We know phenol from probably biology. It's one molecule that people know the most. It's a six-member ring, but includes three double bonds in it. There's the example of dopamine that contains a phenol in it. And there's other examples of that we can think of it, right? So this is capsaicin. This is the stuff that makes your tongue burn when you are eating spicy food. In terms of naming, the alcohols are always going to be named following the same procedure that we know from naming molecules. The only difference in here is that we have to include the alcohol in the main chain, or what we usually refer to as the parent chain. We always identify the substituent, so we do as a second step. On the third step, we assign the location, giving the lowest possible number to the location of the alcohol in the carbon chain. And then we list everything in alphabetical order to be able to name the alcohol properly. Here's an example of how the name changes from pentane to pentanol. So what we do is we change the ending of the alkane from an E to an OL, and that will indicate that there's an alcohol there. By having this oil included in the system, the alcohol is included as the parent chain. Here's an example where the parent chain here is the longest carbon chain that you could have. However, when you have an alcohol, we have to include the alcohol within the parent chain. Therefore, in here, instead of being 8 carbons total, which is the longest carbon chain, it is going to be only 6 carbons total because we have to include the alcohol in it. So we name this hexanol instead of hexane. Here's an example where we're making sure that you give the alcohol the lowest possible number. So the numbering on the left is correct because the OH is on carbon 2, which is a lower number than if you would number from starting from right to left, the OH would have gotten number 6. So always give the location of the alcohol the lowest possible number. Here's a simple example of 3-pentanol because we have the alcohol on carbon number 3. There's two ways to write that. You can put the 3 in front of the pentanol, or you can put the 3 embedded sort of right before the ending of the name for the molecule. So before the oil, you put some dashes and put the 3 in the middle. I prefer to use this one because we don't have to break up the word, and it seems that it's simpler for the students to use this than use that. When you have a range, then the alcohol needs to include the cyclo word in front of it. And in this case, this is known as cyclopentanol. We do not need to include the number one because it's assumed if you have one alcohol in a cyclic structure that that will always be carbon number one. Here's an example of an actual molecule being named. Here we started with the number one where the OH is located, and then we go 1, 2, 3. If we were going to continue numbering, it would be 4 and 5. And the alcohol is given carbon number one, but notice this is cyclopentanol. We did not put the one in front of cyclo because it's assumed it's always one. We do need to indicate the location of the methyl group. So there's 2 methyl groups on carbon 3. So this is 3,3-dimethyl. There are also common names for the alcohols, and these are frequently used as you're working in the laboratory. So isopropanol is what people know as 2-propanol. Terbutyl alcohol is a common name for 2-methyl 2-propanol. And then we have benzyl alcohol, which everybody refers to it as benzyl alcohol, when in reality it's a phenyl methanol because it's only one carbon, so it's methanol. But then the phenyl group is on carbon 1, so we call it phenylmethanol. And because it's only one carbon, you don't have to put any numbers. For alcohols, it is important that you are able to identify whether it is primary, secondary, or tertiary. In this case, the primary always refers to the alpha carbon that contains the alcohol having one R group. And to remind you, the R group represents any carbon source. It could be a methyl, ethyl, propyl. Secondary means that attached to the alpha carbon, you have 2 additional groups. And the tertiary refers to an alcohol that at the alpha carbon has 3 additional groups. These groups could be the same or it could be different. In terms of naming the phenol, we take the phenol as a unit, and that becomes the parent name. So in this example here, phenol is included here within this molecule. We have a nitro group here and a chloro group here. So in order to give the lowest possible number, you assume phenol always gets number 1, and then we'll go in this case clockwise. To give the nitro group number 2, 3, and 4, the chloro gets number 4. We do arrange the name in alphabetical order independently of the number of the position. So this molecule is known as 4-chloro-2-nitrophenol. There are a couple of things that chapter talks about in terms of giving you a little bit of more information about methanol. This is not something I usually ask you in the exams. I usually limit the questions to problems that we're doing, but it is good to have a bigger picture of what this is, because this is how to relate to your daily life. Methanol is the simplest alcohol. We use it as a catalyst a lot, and there's 2 billion gallons of methanol made in industry, and it's actually made from CO2 and hydrogen gas. However, methanol is poisonous, and so we want to be careful with it. We can use it as a solvent, we can use it as a precursor for chemical synthesis and fuel, but you do not want to consume methanol. Ethanol is probably the one that's mostly known. It's usually produced by fermentation of grains and fruits. In industry, you can actually produce it from ethylene, and you have about 5 billion gallons a year in the US alone. Normally, the ethanol that's used for consumption is produced by fermentation and not by this chemically acid catalyzed hydration of ethylene. Ethanol has many uses, as we know. Solvent, all your hand sanitizers contain ethanol for the most part. And obviously people consume ethanol. Isopropanol is the other one that we know as Robin alcohol. It's also made in industry from hydration of propylene. It's used as a solvent. It's also antiseptic, and it's often added as a gasoline additive. What is key about the alcohols is that they possess a relatively high boiling point for the amount of carbons they have. In this example, we have ethane, which is a gas, and it boils minus 89. The boiling point for chloroethane is 12. And then when we get to ethanol, which you're maintaining the same number of carbons, about the same molecular weight, but notice the drastic contrast, 78 degrees versus 12 degrees, right? So at room temperature, chloroethane is a gas, while ethanol is not. Why is the big change in that? Well, it has to do with hydrogen bonding. Hydrogen bonding between an oxygen of one alcohol and the hydrogen atom of the other alcohol creates intermolecular attractions between the alcohol molecules that keeps them together, and therefore when you're trying to evaporate and boil off ethanol, the molecules are holding to each other by using hydrogen bonds. That results in a higher boiling point. Alcohols tend to have what we call the hydrophobic region and the hydrophilic region. Hydrophobic means it hates water, and hydrophilic means it loves water. And so alcohols that contain a fairly large carbon chain, like the one here at the bottom of the slide, has a fairly large hydrophobic region, and then there's its alcohol part, which is only the hydrophilic region. In terms of the ability for the alcohols to be used as an antiseptic or to kill bacteria, they have this graph over here that actually indicates that the best alcohol to use will be something that has 8 carbons for the alkyl chain. That will be more effective at killing bacteria than the ethanol that we use, which is down here on carbon 2. The reason we don't use that is because of cost, right? Ethanol is easy to produce and is available or readily available, but octanol is not. The reason these molecules really work as an antibacterial and also as antifungal is because this carbon chain that's hydrophobic is able to be embedded onto the membrane of the bacteria or the fungus, and in there disrupts the membrane and makes the cells break apart. The key to the alcohols, as the first thing we're going to talk about then in terms of chemistry, is that the alcohol hydrogen can be taken off if you have a strong enough base. So what are the strong enough bases we could use for this? Well, sodium hydride. So if you take sodium hydride apart, the hydrogen with the negative charge will grab the hydrogen, the electrons will go to the oxygen, and that will produce sodium hydroxide, and then a molecule of hydrogen gas will evolve. This reaction is irreversible, therefore it's a good one to do because you create 100% of your product. The other way to do this is to just treat the alcohol with sodium metal. In the presence of the alcohol, they generate exactly the same product as the reaction above. However, we only have half a molecule of hydrogen gas, or in other words, half of the moles. Right? You can't have a half a molecule. You have half of the moles of hydrogen gas. The bases that we need to use to deprotonate the alcohols has to be strong enough. Therefore, when you look at the spectrum here at the bottom of the slide, alcohol's pK is between 15 and 18. So the bases that you need to use have a conjugate acid that has a higher pKa number. Why higher pKa number? Because a higher pKa number means it's a weaker acid, but that means that the conjugate base is way stronger. So we want to have a conjugate base that's strong enough to deprotonate the alcohols. Therefore, we want to use the conjugate base of amines because they have a pKa between 35 and 40. Or you could use alkanes, which have a way higher pKa. The higher pKa usually is not necessary, so we end up using a lot of amine bases. Right? The conjugate base is what we use. The pKa is there just to guide us to explain that, yes, you need the conjugate base of an acid that has a higher pKa. I hope that makes sense. There is a big differences in pKa between cyclohexanol and phenol, and the reason for that is resonance, right? When you take off the hydrogen from cyclohexanol, the negative charge stays on the oxygen. When you take the hydrogen out of phenol, the negative charge that's generated is able to be migrated around the ring in order to produce a more stabilized conjugate base, and a more stabilized conjugate base leads to a stronger acid. Another effect that affects the acidity of an alcohol is by induction. So in this example here, we have a molecule that contains three chlorine atoms, which by induction withdraws electron density from this carbon. Eventually that is communicated all the way to the oxygen, which then makes the conjugate base more stable, which makes this a better acid. There's also an effect that we briefly mentioned when we did acid and bases, has to do with the solvent. In here, these two molecules, ethanol and terbutanol, are very similar. The only difference is we obviously have more methyl groups on terbutanol. And what you notice is the pKa difference is a unit of 2, which means that ethanol is 100 times more acidic than terbutanol. Why is that? It has to do with the solvent. Ethanol is a small molecule as represented here, and there's more molecules of solvent surrounding the negative charge because the carbon part is not blocking it as much. However, in terbutoxide, the carbon part of the conjugate base is relatively large, so it does not allow for many molecules of solvents to sort of cover up the negative charge. And when you're covering up the negative charge, you make it more stable. So because there's more molecules of solvent making this conjugate base more stable, we can go back and say that's a stronger acid because your conjugate base is more stable, which means it's a weaker base, which means you get a stronger acid. Let me say that again. The conjugate base is more stable, therefore is a weaker base, and that makes for the opposite effect. It makes for a stronger acid. The way that we prepare alcohols is relatively simple. There's a couple of examples that we're going to see here. The first method, you can just name this method number 1, is by substitution reaction. So if you take a primary alkyl halide treated with sodium hydroxide, you use an SN2 reaction to substitute the Cl for just the OH. The sodium is not used, it's just on a spectator ion. And we end up with a primary alcohol here. For tertiary alcohols, we can't use this system because you end up doing an elimination reaction instead. So what we do here is we use water, do an SN1 reaction instead of an SN2, and you end up with a tertiary alcohol. So this is method number 1. Do use substitution to make an alcohol. The other method of making alcohols is by addition to alkenes. So this is back from chapter 8. The slide provided by Wiley has an incorrect sections in here. All these sections should be 8.4, 8.5, and 8.6. But if you have an alkene, you can convert it to the alcohol by using these 3 reactions that we already studied for it, right? So the top reaction is hydration reaction and gives you the more substituted alcohol. Same with the reaction in the middle, that's the oxymercuration, demercuration. And the reaction at the bottom gives you the less substituted alcohol by hydroboration oxidation. We have covered this before, so I'm only mentioning it briefly. There's a third method for producing the alcohols that is new to what we have done so far in the class, and this is referred to a method of using a reduction of the carbonyl. So what is the carbonyl? And the chapter just talks about a little bit about electrons and how do we count electrons. For purposes of this exam, you can ignore this slide 28. This is just briefly mentioning that methane has an oxidation state of -4, and if you go to the opposite end, right, you end up with an oxidation state of +4. What I care for the exam here is that you know that as you increase the number of oxygens from methane to methanol, formaldehyde, formic acid, and carbon dioxide, and also that includes increasing the bonds to oxygen, you're oxidizing the molecule. And if you're going backwards, right, so if carbon dioxide is converted to methane, you're reducing it because you're going in the opposite direction. You're reducing the number of carbon-oxygen bonds when we go from carbon dioxide all the way to methane. It's summarized here, right? So they're making a really basic statement saying carbon's oxidation state is increased. Reduction is when carbon's oxidation state is decreased. I'm saying for the purpose of this class, you can look at the number of bonds to oxygen and figure out whether it's being oxidized or being reduced. If you increase the number of bonds to oxygen and including multiple bonds to it, you're always oxidizing the molecule. Reduction is the opposite of oxidation. So you take the carbonyl, which is this group here where the carbon is double bonded to the oxygen, and you reduce this by removing the pi bond, and now you have an OH. And don't forget this hydrogen here. I mean, there's a hydrogen here, right? So there's no hydrogen on the carbonyl carbon. When you do a reduction, this C here turns into a CH. So that's an example of a reduction because you're decreasing the number of bonds to oxygen. The best way to do this catalytic hydrogenation, if you take a cyclopentanone, which is the molecule here on the left, this molecule here on the left, treat it with hydrogen gas the same way that we did hydrogenations on the double bonds, operate the same way, you end up doing a reduction of the carbonyl to get this alcohol just over here. We don't use this very often because it uses high temperatures and high pressure for this to work. What do we use instead? We use this new reagent that you're going to learn from this chapter, is sodium borohydride. In this reagent, what it does, it reduces the carbonyl the same way that hydrogen does. How does it work? The BH4, which is down here, just showing the negative charge, right? If we go back, what happens to the sodium? The sodium is an expectator ion, so we don't need to worry about it. So down here, in the borohydride part attacks the carbonyl, breaks the pi bond to give you this anion as an intermediate, and this reaction is usually done in water or methanol. Once you make the negatively charged oxygen, it gets protonated with the solvent that's already there, and then you end up with the alcohol at the end. So it's a reduction because you're changing the bonds to carbon oxygen from being double to single now. This carbonyl is relatively, well, it is flat, and then the sodium borohydride, which is represented here by the nucleophile, could attack from the front or the back. This is important for ketones that has two different groups attached to it. We call it unsymmetrical ketones. Right, on this side we have an ethyl group, on this side we have a methyl. So if they're unsymmetrical, when you reduce it with sodium borohydride, you're going to get a pair of enantiomers because the hydrogen could be added from the left or from the right, which results in this molecule with the OH on the top, or this molecule with the OH in the back. Another reagent that is used to do reduction, do exactly the same thing as sodium borohydride does, is lithium aluminum hydride. Again, the lithium is an S spectator ion, so all we care is about the aluminum hydride part, but it does the same thing as sodium borohydride. It takes the carbonyl and reduces it to a single bond, a jump. So what's the difference between them? There's only one difference between the two of them. Sodium borohydride is a milder reagent, and lithium aluminum hydride is a much stronger reagent. Because of that, sodium borohydride is more friendly and is used in product solvents like methanol and water. Lithium aluminum hydride cannot be used in the presence of any water or any methanol because it reacts with it too fast. The way the lithium aluminum hydride works, again, is the same way. You have a hydride attack on the carbonyl, breaks up the carbon-oxygen double bond to give this negative charge anion, which then gets on a separate step. We have to add hydronium ions to protonate the oxygen to make it negative, to make it OH. We don't want to have this acid in the presence of lithium aluminum hydride because lithium aluminum hydride would rather react with the acidic compound than add a hydrogen to the carbon-oxygen double bond. Here's an example where we summarize the use of these reagents to give you a bigger picture, right? So this is the time where you step back and say, what is happening? So sodium borohydride here to the right is reacting at the carbon-oxygen double bond only, so therefore you get this heptanol molecule with the double bond intact. Lithium aluminum hydride does the same thing, except that we have to do it in two steps. First is the reduction step with lithium aluminum hydride. And then to stop the reaction, then you add water as a separate step, and that's where the OH, the hydrogen on the O alcohol is going to come from this OH. In the first method, the hydrogen from the OH that is on the OH comes from the methanol. But this could be added together, but in this case you cannot. On the left side of the slide, we have the alternative way of reducing the carbon-oxygen double bond by using hydrogen gas. But noticing here that when you do reduce the carbon-oxygen double bond to get the alcohol, you're also reducing the carbon-carbon double bond to make a single bond. So this is a great reagent, but it's not selective, right? It doesn't select for the double bond versus the carbon-oxygen double bond. These reagents do. Sodium borohydride and lithium aluminum hydride only go after the carbon-oxygen double bond and leave the double bond intact. The great thing about these reagents is that you can modify them. How do we modify them? Well, take these R groups that are represented here, and they don't necessarily mean at this point that they will be alkyl chains, even though that's what we've been talking about. You can replace this R group with alkoxide, cyano, or really, really big groups in it, and you change the dynamics of this reagent. Going to the lithium aluminum hydride and why it's different than sodium borohydride. What lithium aluminum hydride is much stronger. And because of that, you can reduce carboxylic acids and esters. You need an excess of it in order for you to work, especially if it was in water. So you treat it with a bunch of lithium aluminum hydride to reduce anything that's there to give the corresponding alcohol. We don't have to worry about this mechanism on slide 41. I'm not going to ask you to do this mechanism. It's just showing how the aluminum hydride attacks the carbonyl, which is the same way that it does it for the ketone, except that we got an oxygen methyl group in it, and that gets thrown away. All right, we have this preparation of diols. I'm skipping that part. The only difference is when you want to make a diol, which means two alcohols in it, you need to have twice the amount of carbonyls in it. That's all what this is. Here's a summary example, right? If you have two carbonyls, then you get two alcohols, and we call that a diol. Diols. The other way to get diols is to, which will be sort of a way of making alcohols in a different way. It's by addition to the double bond using these reactions with which we did back in chapter 8. This is the anti-dihydroxylation and the syn dihydroxylation. So look that up, and so you don't miss this method for making alcohols. Sure, it's making a diol, but it's still considered an alcohol. I'm gonna stop the recording here because the next part really represents the other half of the class.